This is a screencast on the difference between continuity proofs and uniform continuity proofs. So first, a brief reminder of the definition of continuity. F is continuous at a point C in A. And I want to point out that here it's continuous. In fact, maybe I'll do this. The key thing is it's continuous at C. So you don't just say a function is continuous. Sometimes we cheat a little bit and say, oh, the function's continuous everywhere. But what we really mean is it's continuous at every single point in the domain. So you really, if you really want to be proper about it, you only talk about being continuous at a point. And if you want to be a little lazy about it, which mathematicians often are, you say, oh, it's continuous at every point in A, which we shorten to is continuous on A. So it's continuous if for all epsilon there exists a delta such that for all A, x minus c less than delta, f of x minus f c less than epsilon. Okay, so that's one difference, is continuous at C. F is uniformly continuous on A. So to compare and contrast, continuity you really talk about at a point, and uniform continuity you talk about on a set. So that's difference number one. And then it looks very similar. For all epsilon there exists a delta such that for all x and y in A, basically the same thing, where you just replace C with A. The second major difference is here I have x and c. Here's c. Here's x. Notice that one is defined before we ever define delta, and this one is defined after we define delta, because here's delta right here. So let's contrast that. Uniformly continuous, right? There are no points here. There are no points here for all epsilon. Oh, now we have our delta. And now we can define both points after delta. We only define points after delta. And that has a big bearing on how we prove continuous proofs. So a generic continuity proof would be let epsilon be bigger than 0. I'm not actually proving anything. I'm just giving a general form. And C belong to the domain. That's basically your first step for a continuity proof. Then you might say let delta equal whatever actually works. Then for all x belonging to A such that x minus c less than delta, we have, and now here the whole point is we get f of x minus f of c is less than or equal to da 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 is less than epsilon. That's the whole point. So that's one difference, and I'm going to spell another difference later. So the key thing, once again, is that here you have one c before delta, and here you have an x after delta. Let's look at uniform continuity. Just say let epsilon be bigger than 0. I'm not going to define a c because I need to define delta first. Then you might say let delta equal whatever you let it equal to make it work. Then you say then for all x and y belong to A such that x minus y less than delta, we have, and then the same thing, f of x minus f of y less than or equal to da 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 less than epsilon. So now, once again, notice the x and the y are both defined after the delta. So that's the big difference in continuity proofs. Another difference is at some point you might have an intermediate step down here that says, like, I don't know, you might get xy times x minus y less than or equal to, sorry, xc times x minus c. And very similarly here, you might have xy times x minus y. Notice that x minus c and x minus y are good because that's your delta. So if here you have xc, the key thing here is that c is constant. Let's put absolute values around them. C is constant, so you don't need to do anything with it. Neither of these are constant. So this x you would define in terms of c. So you might replace that with like a c plus 1, or like a, 3c over 2, something like that. The x and y you'd have to define in terms of your a. So if your a were like 4 to infinity, you might replace them with 4.